the net now. So would you like to introduce Dr. Levin, yes, or shall I?
No, I like to introduce her because
sure,
she's my mentor. And can we bring his slides up first? So we have, Victor, are you online? I see him. He looks muted to me. He's under Ellen. Could someone unmute Dr. Levin? He's talking, but okay.
Yes. You can hear me now?
I can hear you, Victor. Thank you very much.
Yeah.
Can we put Dr. Levin's slides up, or can you bring your slides up, please? And while he's doing that, let me just introduce Dr. Victor Levin, which could take a very long time. I have his CV in front of me, which is quite lengthy. It's 28 pages long. Victor Levin has had 404 articles that he has published in the field of neuro-oncology, 63 book chapters, 2 books. Dr. Victor Levin is, what's interesting, in 1988, neuro-oncology was somewhat of a new subspecialty of oncology or neurology. And when I finished my residency program, I looked for the best neuro-oncologist in the world. And I said, I'm going to do my fellowship with him. And I was very happy to see that he was in San Francisco. And so I applied for the program. I was accepted. But unfortunately, he left to go to Houston, MD Anderson. And so I switched from San Francisco to follow him to Houston. And I think if I remember right, I was his first fellow in Houston, Texas at MD Anderson. Dr. Levin is, in my opinion, the father of neuro-oncology. There may be 2 other doctors or neuro-oncologists of his quality who really founded the Neuro-Oncology Society. And in fact, Dr. Levin was the first president of the Society of Neuro-Oncology, which has grown into a very strong academic and clinical society to support all neuro-oncologists, including radiation oncologists, neurosurgeons, basic scientists, and medical neuro-oncologists. So, my affiliation with MD Anderson lasted a short time, but I've kept in contact with Dr. Levin and kept an eye on his research. And it was really truly an honor that he accepted this talk for the Mind Neuroscience Professor Lecture Series. And that's my introduction. I could go on. And I'd like to thank Dr. Levin. Do you have your slides up, Victor?
I do, but I haven't figured out how to. But I'm also unmuted, aren't I? Yeah.
Yeah, we can hear you. We can hear you completely.
Well, how do I get my slides on?
Share screen, maybe.
I don't see any directions. I don't see anything in my Zoom.
At the bottom, you should have participants, chat, share screen. It's the green one.
I'm going to join meeting again to see if that'll do it. No.
Okay.
I can't do it.
I do have your slides that you sent.
Yeah, but I can't. The only thing I can do is I could leave the meeting and come back.
Why don't you do that?
Maybe I'll do that.
Do that. In the meantime, if somebody has a question to Dr. Laurent, Dr. Erush, about the previous lecture, we have a few minutes. I do have a question, Laurent. It's interesting that the way that brain tumors, glioblastoma, is treated in Hungary is similar to the United States, but there is some very interesting differences. For example, when you have radiation necrosis, we don't give steroids. We actually give bevacizumab or Avastin. That's one. Number 2, you have MRIs every 3 months. In America, it's every 2 months. Any reason behind that?
All right. Am I up now?
No, I don't see you. No, I hear you, but we don't see you.
Well,
I'm there.
Yeah, I see him, but can you see?
I will share the screen right now. Okay.
Yes.
Great.
Yes, Victor, we have
I'm
your.
doing it. I'm doing it. I'm
screen.
Okay, let me just
go back to slide 1.
Hold on. Let me just make sure that. There we go. Now from current slide. There we go. Perfect.
Beautiful.
All right. Thank you very much.
Did you hear my introduction?
I heard the introduction. Thank you very much.
Do you want me to go on and on or stop right there?
Nah, you better stop. You better stop.
Okay, thank you.
All right. And so the last time I even did anything in Budapest was 1977. Many of you may know or not know, I worked early on with dianhydrogalactitol and dibromodelsitol. Dianhydrogalactitol must have been the national drug of Hungary at the time. It was from Canoin. So let's go on and talk about a new drug, eflornithine, which is really an old drug. So these are my current positions. I'm sort of semi-retired, but still working. My disclosure is important because I'm a co-founder and senior medical advisor to Orbis Therapeutics, the company that is trying to commercialize eflornithine in the United States and Europe. We all know, and I think it's probably a waste of my time to show you this slide, that what we're dealing with are relatively rare tumors. In fact, by the definition of a rare tumor, almost all our brain tumors fit into the category of rare tumors. And what we're going to be talking about is not so much glioblastoma as the anaplastic astrocytomas, and probably by inference, maybe the lower grade gliomas. At the time that I drew up this slide, there were not very many gains made in the treatment of anaplastic astrocytoma, either in the United States or in Europe. Some of the gains that have been made since then have been more gains in classification than true gains in therapeutic benefit. So now let's look at the progression of treatment and the progress over the past 40 years or a little more. And the thing started with, on the top you see therapies, and on the bottom you see physical or radiologic and surgical benefits. The physical things versus the drugs. We see that CCNU and BCNU came out, PCV, temozolomide, and in the United States at least, Avastin or bevacizumab for glioblastoma, but not as an anti-cancer drug. And then Optune, the treatment field approach. And we've seen also the advances in CT, MRI, intraoperative mapping, the change from whole brain radiation to limited field radiation, the advent of radiosurgery, conformal radiation, and in IMRT or intensity modulated RT. During all this period of time, there have been enormous increases in our understanding of the molecular genetics of these tumors. But what have they given us? They've defined classifications that predict response to radiation and DNA alkylating drugs. They have not led, unfortunately, to a new drug for the treatment of gliomas or medulloblastomas. And my quest during my most of my professional life was to bring forward a new drug, a new treatment that could be used to improve the survival of these patients who have to rely on alkylating agents and radiation. So let's start with eflornithine. What is eflornithine? Well, it's really known as DFMO, difluoromethylornithine. It was originally developed for the treatment of trypanosomiasis by Richardson Merrill in their laboratories in Alsace. It's used today, and it has been used since the 70s. It was patented in the 70s, but it's been used since it was developed and used originally in Africa. So it's probably been in use, I don't know, 30, 40 years, maybe 35 years. It's a small molecule, it's water soluble, it's orally bioavailable, it's not metabolized, it's cleared by renal elimination, and you can chronic dose it with elimination half-time of about 4 to 8 hours. What's nice about the drug is that it's an irreversible inhibitor of ornithine decarboxylase. It's a suicide enzyme inhibitor. And this is an enzyme that catalyzes the first step in polyamine biosynthesis from ornithine to putrescine. Ornithine goes to putrescine, gets activated to spermidine and spermine. And as you can see, they're very simple carbon-nitrogen compounds. And what they do, though, is they intersect DNA and RNA stabilization. They have a, let me get rid of this. So hold on. They have the modulation of chromatin structure. They have an impact in transcription and translation, membrane stability, ATP binding, ion channels, singular transduction, cell growth and proliferation. What it really means is it can do multiple things, and what the heck it's doing in the tumor cell for certain is not always clear. Here's an association map of ODC. Oops. I'm trying to move, there it is. ODC, ODC1 here, DFMO here, and DFMO only, of course, works through ODC. But what we can see is an association with oncogenesis, the maintenance of the transformed phenotype. And the other interesting thing is in virtually all tumors studied, adenocarcinomas, gliomas, melanoma, when malignancy grade increases, the ODC level increases. But it's not like amplification, where we see 10-fold, 20-fold, 100-fold changes. Here we're talking about 1 or 2-fold. And so it's very unusual, okay? It's an activation of a dimer. The proto-oncogene RAS and MYC are downstream pathways that control ODC transcription. Inhibition of ODC can revert transformation, can cause cell cycle arrest, and it can inhibit invasion. If you look carefully at some of the oncogenic transformation pathways, you can see that ODC is down here on the bottom. So through the receptor tyrosine kinases, the PI3s, the RAS, the RAC, MEK, mTOR, ERK, eventually to get a cell dividing, you will utilize ODC to one extent or another. If we look at the research dealing with ODC and DFMO over the 4 decades, it's very instructive. Ornithine decarboxylase was first discovered actually in a C6 glioma cell by Yuri Bacharach. And why he studied that cell, he was just studying it at the time when he was developing the assay. But DFMO was discovered in '78 for trypanosomiasis. We started studying polyamines with Larry Martin in 1980. In 1981, we used it with BCNU in culture. Then we used BCNU in IC tumor models. Then we used it, and then I studied the pharmacokinetics in the CSF and the tumor. And then we started clinical trials. I did a randomized clinical trial through an FDA orphan drug grant to look at DFMO plus DFMO and MGBG, or methyl GAG, which is another polyamine inhibitor. And we'll talk a little about that. I've used it with BCNU in '87. We initiated in '88, '92. We initiated very large studies with DFMO PCV for gliomas as part of a cooperative trial. Published the DFMO studies in glioblastoma, anaplastic gliomas. Started a company called VBL Pharmaceuticals, got orphan drug status, couldn't raise enough money. My son developed a company called Orbis Therapeutics, raised enough money. We got FDA breakthrough designation as the first drug to get breakthrough designation for a brain tumor. And we're into pivotal phase 3 trials for recurrent AAs. Now I want to digress just a little to provide a teaching moment. I'm going to talk a little about pharmacokinetics and pharmacodynamic considerations as they apply to the field, and then we're going to go specifically to use eflornithine as an example. So the first thing is there was a there's been a lot of human pharmacokinetic studies, so that's quite clear. And we know from that you can get levels of, 300, 400, 500 micromolar at doses of, say, 3 grams per meter squared. In these studies, it showed that the drug is not metabolized, not protein bound, and the elimination half-time, as we talked about, was 48 hours, which originally was used in a 6-hour schedule, but I changed it to an 8-hour schedule dose because it was much more convenient to patients, and I had better acceptance of the treatment. So now let's look at the basic concept of permeability and transfer constant. So the capillary transfer constant, K1, differs from the permeability coefficient by virtue of the fact that we have surface area as part of the measurement in the permeability coefficient. Transfer constant deals with the mass movement of a molecule, but does not consider the surface area of the capillaries into the tissue that it's going. So here we see on the x-axis, the brain Ki. So this is the transfer constant. And on your right, you'll see a big list of drugs that I've studied for this. All are radio-labeled except for, I think, the temozolomide, which was done by PET and C11. Number 17 is temozolomide. Number 11 is, of course, DFMO. In the tumor side, you see that in here we're doing the same animal species, rat, and we're also doing the tumor in this case. And we're looking at the entrance of these molecules into the tumors. And as you see, the tumor levels in this area are much higher than one would expect. One would expect if the brain and tumor are the same, that the transfer constants would show a convergence in the centers, and they don't. And the reason is that tumors have lower blood flow than brain, and these molecules are diffusion limited. These molecules are blood flow limited. So tumor levels will be higher for most drugs that are large molecular weight than they would be normally seen in the brain. Some years ago, I developed this a model based on experimental research that I've been doing in all sorts of tumor models. And here we can see that capillary permeability in the necrotic center is very low. Well, that's common sense. Also common sense is that the area that has the high perfusion ring that we see with all forms of imaging from nuclear to CT to MRI is high. What wasn't so clear and wasn't so obvious until I had done my experiments was that the brain adjacent to tumor can have a lower permeability actually than even the brain. And so probably it's a function of some kinds of pressure gradients that are exerted on that area. Now, it was only recently when I collaborated with Ben Ellingson and published a paper in Neuro-Oncology on drug permeation that we actually developed a system that somewhat revalidated at least a good deal of what I've just been talking to you about. And here we have here we're looking at the K-trans map, okay? And this is a K-trans map that is corrected for pixelation and is looking at the movement over time after a bolus injection. And I think let's just focus for time on this bottom one here, E and F. And here we have central necrosis, and then we have this enhancing tumor. The enhancing tumor has a variable permeability, some of which is a function of the fact that it's a bigger area and more heterogeneous than the area that I could study with radioisotopes, where I'm measuring at 0.75 millimeters or 0.5 millimeters between cuts. But it's going, as you can see, though, it is definitely going down, and then of course it gets lower in the brain. So it doesn't completely validate the exact model I'm using, but it gets close to show how important this permeability can be. Now let's change gears for a second, and we're going to quickly go through the following. We all know that astrocytomas don't have permeability of gadolinium contrast because we don't see it. When we get to anaplastic tumors, we see a little of it, okay? And when we get to glioblastoma, we see a lot of contrast enhancement, okay? But what is the truth? The truth can be found if you look into the literature. There have been people who've been studying quantitative K-trans values in different tumors. And the studies are very interesting because they basically conclude that there is a permeability change in all forms of gliomas. So on the left here, we have the brain coefficient from my studies, okay? So this is what brain is for a molecule like this size. It's also validated in their data, okay? You look for a grade 2 tumor, it's 0.042. Well, that's much higher, 0.124, 0.174. So the bottom line is that all gliomas have an increased permeability. The fact that we can't see it is irrelevant. They do have increased permeability. So now if we take that same K-trans curve, graph and we superimpose the values for these permeability coefficients, we see brain down here, which is basically almost perfect. And here's grade 2, grade 3, and grade 4, okay? So what it gets to is the concept that even with a larger molecule, you're going to have entry into many of these tumors under the right conditions. So let's talk about the right conditions. So early on, when I was at UCSF, I anticipated the fact that this drug, which we could give chronically, would achieve a high enough level of drug into the tumor ends of the surrounding brain to be effective. But I had to prove it. So what I did is I set up an experiment where I harnessed rats with an intracerebral 9L tumor. They're freely moving in a cage. They're infused with labeled and unlabeled DFMO to maintain a steady state plasma level for 1 to 4 days, okay? Then I euthanize them, analyze them for C14 DFMO in tissue to plasma. And I'm doing this in a very specific way that's outlined and have used for years prior, where the brain is rapidly frozen. I get sections that are 0.75 millimeters across. So it's a very precise and reproducible methodology. And what did I find? I found that it was very easy to attain a brain to plasma ratio of over 1 with this kind of scenario. And so I felt that this validated the use of this drug and the concept that one has to be careful about when you're talking about brain penetrance. It's different than brain permeability, okay? So brain penetrance, I'm sorry, not brain penetrance. When we're talking about penetrance here, we're talking about, say we're talking about blood-brain barrier permeability to normal brain in the brain adjacent to tumor where infiltrative tumor is. When we're talking about permeation or penetrance, we're talking about the penetrance of a drug into the brain adjacent to tumor and the brain and distant from the tumor. And so the following are the concepts that I developed to define what would be usable as an agent. It's not only DFMO. You could use some of the ADC conjugates too if they were correctly, if they gave the correct physical characteristics. So it really comes down to you want a drug, go to 3. You want a drug with low plasma clearance, low protein binding, the ability to sustain the plasma drug level for days to weeks with little systemic toxicity. And you've got to have strong or irreversible target bonding because you want to stop the drug periodically, okay? And so this is the concepts that we developed, and I think they basically hold. The next part of it was, will we be able to reach tissue levels that are high enough? Now, these are post hoc. these weren't done at the time I did my original studies. They were done more recently to justify further to the regulatory community and the physicians who are going to be in the STELLAR study that this drug actually will reach and achieve a therapeutic level, and that therapeutic level is consistent with what we believe to be the efficacy of agents needed for treating brain tumors. So on the right, you see these three tumors. They're all CNS tumors. These are adenocarcinomas. In the IC tumors, you can see that it's somewhere between 74 and 350 is the IC50 in the three-dimensional agarose colony assay. You never want to study these brain tumors and develop IC50s against monolayer cells. And we know from the published literature that the levels we could get would be at least this high. So we said to ourselves, okay, this further justifies that our dose is correct, our method of deliveries are correct, and we're going to reach therapeutic levels. So now let's look at the trials. First, they started with phase 2, carcinoma trials, melanoma, leukemia, and I started doing the glioma trials. Now, there's a big disparity between the number of patients that I studied and the number of patients in the literature. And I think part of it was a difference in expectations. The company just made drug available, and it was used in the usual phase 1, phase 2 mode. And it did have activity. If you look at the PR, CR, it's not so great. And to be honest, that's what the medical oncology community was focusing on. If you didn't have something that was really obvious, like a reduction in tumor size, we don't want it. But those of us who deal, yes? But those of us who deal with brain tumors are frequently very, very happy if we can just stop the damn tumor from growing. And so stable disease turned out to be important for us. So whereas these people thought, oh, it's not worth pursuing it, those of us who were thinking about brain tumors are saying, boy, this isn't bad. This isn't too bad, and it's not toxic, and we could combine it. So the glioma trials took off. The company continued to provide drug even after its 6th iteration as the 6th company that picked it up. And so we moved forward with, initially our endpoint was time to tumor progression. They didn't talk about progression-free survival in those days. We went to overall survival, and we did it alone in combination with methylgag, as we talked about PCV, BCNU. Let's talk through some of the studies. So in the randomized single-arm study, which came a single-arm study, it was actually a randomized 2-arm study through an orphan drug grant with the FDA. We were going to look at eflornithine plus mitaguanazole. What happened was unexpected. The mitaguanazole addition produced hepatotoxicity, and we had to stop the study after only 25% of the patients had been accrued. The FDA allowed us to continue the single-arm study at that time because they basically had no option. The study had patients who failed radiation, had failed radiation plus minus chemotherapy. And this is the breakdown of the kinds of patients that were in that study. But also I'd like you to keep in mind that in those years, the diagnosis of glioblastoma required pseudopalisading necrosis, and just having vascular change did not define glioblastoma. So as a result, about 20% of the anaplastic tumors in what I call the anaplastic glioma group or the AG group today would be classified as glioblastoma before we have the advent of molecular markers just based on the light microscopy appearance. And what we found is not spectacular, except for the fact that even of the 18% of the patients in glioblastoma who received an R plus SD, it got to 35 weeks after after failure. When we looked at the anaplastic gliomas, it was pretty good. 45% of the patients had time to tumor progression that was almost a year. So here, for instance, is some of the data. And let's look only at this group here to make it less complicated. So here we're combining the anaplastic astros and the oligoastros. We have a median progression-free survival of 18.9 weeks, because I'm recalculating this in 2006 rather. If we look at the people who had response and stable disease, it's 45 weeks. So for a cytostatic drug, not a cytotoxic drug, for a cytostatic drug, this is pretty good. And based on this, my son and his colleague got interested in pursuing this compound. And they asked me to do something that I hadn't thought about before, and that is look at survival. We rarely do a phase 2 study and worry about survival. It's really a short duration study. We're looking at progression-free survival, time to tumor progression, some indication of activity. But in this case, they were looking for something that they could hang their hat on for statistics to raise money with venture capital and to get agreement from the FDA that we could go forward with a treatment for recurrent anaplastic astros. So I, as a good son, I dutifully went in and looked at the data, and had been kept current by the MD Anderson Data Office, as well as the University of California, San Francisco Data Office. So I had just called them up and said, could you give me the data? Well, they're providing data that's about 8 or 9 years later than the study that I had closed. And so how good is it? Okay, so here's the eflornithine, in the blue is the eflornithine survival data, okay? Chamberlain was doing a study at the time looking at CCNU for recurrent anaplastic astros, and he had 10 months. Wong published this very nice paper with to look at progression-free survival, trying to figure out how you power glioma studies, glioblastoma, anaplastic astrocytoma studies. And I was a co-author in the study, and when I'm looking at my database for the survival data here, I realized that those patients, many of those patients are in the Wong database. So I take those patients out of the Wong database. And so this is the curve from the Wong database minus the eflornithine patients, and it's 9 months. So it's clear that the benefit is from the eflornithine patients. This is a very strong signal. Oh, furthermore, I went back into this data thinking, oh, maybe there's something funny going on here. Maybe they got treated with something different. Maybe they had surgery, radiation, et cetera, et cetera, et cetera. And what I found was that the vast majority of patients in our study who had failed DFMO never received another form of chemotherapy, okay? So this is very, very exciting because my follow-up here, if you see, is 10 years. So then we did a phase, then we did a phase study with, no, this is just to show comparability, that's true. Here I'm showing you that eflornithine as a single agent isn't really much different than temozolomide. PFS at 12 months, 25%, temozolomide, 24%. But median survival is much higher than the literature. Now, phase 3 studies, so when I moved to MD Anderson, I wanted to get some real strong statistical validity on this. And the community oncology program at the time was looking for a trial to use in multiple institutions in the private sector. So I wrote this protocol for them because it would kill 2 birds with 1 stone. It would give me the kind of statistical data I wanted to either prove that this drug is that good and I should go forward with it, or it was just a fluke and we're not going to go forward. Because as you know, sometimes even strong signals in phase 2 studies don't turn out to pan out in phase 3 randomized trials, big trials. and this one will. So here's the combination we used, eflornithine plus minus PCV. And we have two protocols, one for glioblastoma and one for anaplastic gliomas. And so we're just going to look at the anaplastic gliomas. And here we have the demographics of these patients. They're about the same. And we look at the toxicity, and it's not particularly a toxic agent. We know how toxic PCV combination is. So I subtracted out the two-arm toxicity percentages, and you can see it here. And clearly we had some increase in thrombocytopenia, and also we had ototoxicity, even though ototoxicity wasn't significant because radiated patients sometimes have loss of hearing anyway. So it looks like it's a pretty safe drug. Diarrhea is normal with this agent because the osmotic load of the amount of drug you're taking. You're taking orally about 20 grams a day because most of it is cleared. So what do the curves look like? Well, the curves look like when I published in 2003 that they diverge and stay apart for years. Here the difference is about 2.8 years difference in progression-free survival. Okay. When we looked at the anaplastic glioma patients, in a second, where am I? Oh yeah, this is the published data, okay. And this is the data after I look at it years later, because I hadn't gotten enough survival data when I published originally in 2003. So for the purposes of trying to decide if this drug is should be pushed for another study, we did these studies. And again, I leaned on the databases at MD Anderson, and they said, oh no, because I had never closed the study because I had thought I wanted to get survival data. So they basically in a week sent me the updated data, and I looked at the data, and the differences are 4.2 and 6.7 years. But by log rank, there's no difference. And the reason is, and I don't know if there'll ever be, because these curves are never going to cross. The therapy just lifted for a time the death curve, and when the therapy stopped, because we only treated for 12 months, it continued. Here is where we take out the anaplastic astrocytomas, and here the log ranks a little better, 0.07. In fact, this might be a Guillain-modified Wilcoxon. But what we did see, Ken Hess was very clever, and he said, there's got to be, let's look at the beginning of the treatment because everything seems to be hinging on the beginning of the treatment. So he looked at the hazard rate analysis, and he found that the impact of therapy, which is given only for 1 year, was experienced by the patients up to about up to 3.5 years. I think it's about about 2 to 3 years. You can see the peaks here. And if you look at the hazard ratio for the patients, now this data from the PFS is from the 2003 paper, because you don't do a PFS hazard ratio 10 years afterwards. But the overall survival hazard ratio is from the data 12 years later when we do have survival data. And again, you can see that the biologic effect, again, is in that same window, okay? And it's even better now. So the problem is the drug was never given long enough. Had we given it long enough, anybody from across the room would have said this drug is great. So we had to move on. So also at that time, from a research perspective, I'm still trying to understand what defines, can I get a tissue marker? Can I get some measure that's going to tell me how good, who's going to respond best to treatment? I know the glioblastoma patients don't do well. I know the anaplastic patients do better. So I wanted to know about the ODC levels and if they correlated with eflornithine or DFMO anti-tumor activity. And to do that, I had to develop a fluorescent assay to measure ODC activity. ODC is an enzyme that becomes activated when it becomes a dimer. And it would be impossible almost to measure its activity in tissue based on the kinds of assays that were used. But I thought there was one other way of doing it, and that is my friend Lisa Shantz had developed a heart model of ODC, which overexpressed the ODC protein. And so she would run an assay on the heart tissues. And so I developed an assay based on a fluorescent antibody that was specific to the activated dimer. And as you can see, it's not a bad correlation. ODC activity is on the x-axis, and the grayscale and super mean grayscale intensity is on the left. And so we felt that's a good enough assay. So we went forward with that. And we went through this. And now ODC activity was interesting as I'm doing these studies. So what we did is we did tissue microarrays on tumors. And so in this tissue microarray, we would basically do fluorescent microscopy of this specific antibody in every single tumor cell in the tissue section. And what we found was also that depending on where I took the experimental tumors, it would determine whether the ODC higher in the cytoplasm or in the nucleus. Logic says if it's in the nucleus, it's having to do with dividing cells. And if it's in the cytoplasm, it's probably having to do with invading cells, which would also take advantage of ODC for, say, RNA function. So here's a good example. Cytosol is on your left, nucleoplasm is on your right, okay? And so I think that that is the proper interpretation. Nucleoplasm division, cytoplasm invasion. We looked at different tumor distributions in different tumor cells, and we saw that there was differences in the way these tumors grew. And what's interesting is the SNB19 tumor was the only one that had increase in cytosol over nucleus. So again, nucleoplasm, DNA function, cytoplasm, RNA function. That's at least our interpretation. If we looked at different tumor types, anaplastic, astro, oligoastro, oligo, and glioblastoma, we found, of course, that these tumors had different median ODC activities, and which is what you'd expect. What was not expected, though, is that the oligos would have a higher level when they're actually not as malignant as the anaplastic astros. But I think part of that is a reflection of the fact that even the labeling index is higher in anaplastic oligos, and there must be more cell turnover in an oligo than there is in an astrocytic tumor. Okay, and this just shows that I wanted to see if there are other relationships I could get out of the database from that PCV study. But after a decade, when I went to go back to the data to get the information, I could not get all the tissue blocks to do the study. And Laszlo will probably remember we had a huge flood in Houston, Texas, and it damaged many of the facilities, and it destroyed the entire path storage area for Baylor College of Medicine, which had provided us a lot of patients at MD Anderson at the time. And so between the flood damage and physicians being contacted for tissue blocks and not willing to send them, I couldn't get many. But at least as a preliminary look, I started looking at the breakpoint for ODC activity. And it turned out that the breakpoint was about 3.3 nanomoles per 30 minutes per microgram protein. And so I said, well, I wonder what the progression-free survival might be for patients in these two categories. And it turned out that there's a huge difference if you're above or below that break point. And the break point didn't have values that were close to it. It was just a break point, and the values were either much lower or much higher. And you can see there's a huge difference in PFS. But so what? I mean, it probably, to my mind, I said it probably was a function of the true malignancy of the tumor. Because remember, we're doing these studies before we have any molecular genetic correlates. So all anaplastic astrocytomas, as you know, aren't equal. So years after that, even when they discovered IDH1 mutation, I asked Ken Aldapi, well, who was still at the MD Anderson at the time, to pull up my a tissue array that I had left there and to compare it for IDH mutation. And so he looked at wild and mutated. And in this data set, you can see that 22 of the patients had mutated and 29 had wild. Okay. I looked at the difference in wild and mutated and looked at PFS and overall survival. And as you would expect, this is basically sort of preliminary information, and I never published it, but it shows that if you're IDH mutated, you do better on eflornithine. If you're with respect to PFS and with respect to overall survival. And it's no surprise. These are the people who work with me on this project, these projects and these many papers over a period of a decade. Now we're going to quickly talk about the Orbis Therapeutics Stellar study, because that may have an impact on your practice in the future, I'm hopeful. So when approached, the FDA and the EMA required that we have one more controlled randomized phase 3 trial before they would give approval. Now, they have both written to the company saying that if this trial works, the drugs are approved. So most of the other parts of the equation that are needed for approval are in place. We picked up only recurrent AAs because it was the only way we could get enough focus and to be able to get enough behind the presentations to convince venture capital to put money for this into the study. What I realized, but on one level, but didn't realize on another level, was how really rare recurrent anaplastic astrocytoma really is. Because as you know, many of them, maybe if not most of them, recur as glioblastoma. So the trial design was really straightforward. It's an A versus an A plus B design with an expectation that the A plus B will improve median survival by 50%. So that's a huge test. And the study has a target hazard ratio of 0.667, a median improvement of 6 months. It's powered to provide statistical significance if the improvement is less than 6 months, but more than 4 months. It requires patients be treated at first recurrence progression, after irradiation and adjuvant temozolomide. And that at recurrence, the tumor has to be first recurrence as an anaplastic astrocytoma. That means that there's attention given to the appearance of the MRI, the amount of necrosis, the appearance of the lesions, etc. So it's not perfect, and we know that some glioblastomas are going to get in, certainly because we know based on the molecular markers today that many anaplastic astrocytomas are 2 steps away from being glioblastoma. Study is powered for 340 patients in a 1-to-1 randomization. It's open in 8 countries, and it's accrued 85% of patients needed. And we hope that we might get the first statistical readout, and my hope is the only statistical readout we'll need at the latter part of the first quarter of 2021. And that is my talk, and I hope you enjoyed it. And now, how do I get rid of this? So I stop share. There we go. All right.
Thank you very much, Victor.
That's it.
So, Victor, thank you very much. If you don't mind, I have just a few questions. You know, we were part of your study at the Dent, but unfortunately, every case that recurred, our neuropathologist, even though I thought it was a recurrent anaplastic, called it a glioblastoma. So you stated that 20% of recurrences are glioblastoma. Don't you think that number is actually much higher?
No, I'm saying in my study, they probably were.
Okay, all right. In real life, it's really very uncommon to see an anaplastic progress to a anaplastic. We know it stayed the same. We've seen, my pathologist is always calling it glioblastoma even without endothelial proliferation, without necrosis.
Okay, so now here's the difference. So what we're asking of the pathologists is that and the radiologists, okay? So if you're going to have a reoperation on a patient, then obviously it's not the radiologist. But if you have a reoperation, then what we're asking of the pathologist is, does the tumor have the phenotypic appearance, the light microscopy appearance of an anaplastic astrocytoma? We're not asking them to evaluate the molecular probes that would tell them that it's really going to be a glioblastoma. So that becomes the separate issue. And we've had cooperation from all the major pathology centers in the United States and Europe. Everybody agrees, okay? We all know that phenotypically, many of these tumors will be glioblastoma. But we don't know in our clinical trial until until the code is, you know, the blindedness is unblinded, is how well we're doing against IDH wild tumors, okay? Because we have about 40% of the patients in the study are IDH wild, and that's by original path, okay? So, okay, so that's the conundrum. Clearly, this is an easier study to do up front. And originally, I wanted to do a temozolomide plus minus eflornithine, and I thought that would end up being the treatment of choice for these tumors, because one of the other things we've published on recently is that eflornithine can damp down mutations produced by temozolomide, so it actually adds safety to it as a treatment. Unfortunately, no venture capital we wouldn't be able to find any venture capital to do a study that'll require 10 years.
Yes, understood. Do you have any questions from the audience?
May I have a question?
Yes.
Hi, Dr. Levin. My name is Loran Derős. I'm from Budapest, Hungary. Neurosurgery.
You know, my name isn't Ellen, too.
Yeah, right? You are Ellen, I know. Yeah.
My wife used it last, right?
Yeah. You started to observe the IDH1 mutation group in your study, and do you have a look at the 1p19q codylation group, or somehow?
Oh yeah, sure. I'm not showing data. It was too small a group, but I don't know if I have I could pull up. I don't think I could pull up a slide fast enough. But anyway, it works against oligos, no question. Okay, oligos are not in this, so you can be sure of that. The pathologist, the referee pathologist was Jan Brunner, and she doesn't make mistakes on oligos. And she probably went the other way around, but we know that this works really well in oligos, okay? Because in the oligos study, I think I'm my median for oligos might be, I don't know, it's in my paper, but it could be 16, 17 years, something like that. It's huge.
Yeah.
but it's not enough. It wasn't, it's in the, I think I mentioned it in my paper in CNS Oncology, my review, but I think it's a really high number, but I can't do much with it because it's, you know, it wasn't designed to be an oligo study. And if somebody wants to do an oligo study, just keep in mind, it'll never end in your lifetime.
Yeah.
Good point.
And what is your protocol for insular gliomas, but not low grade, but malignant gliomas in the insula?
Depends on where I'm working. When I was working at MD Anderson, Fred Lang frequently would operate on them before we treated them. Elsewhere, you know, people will do it, but it's not something that all surgeons want to do. But frequently, we used to get resections of insular tumors. Yeah, when possible. I mean, you can't just say all insular tumors are resectable. They're not.
And do you feel that still gross total resection has a great influence on outcome in these locations?
You know, what can I say? Do you really think it's possible that somebody could do a gross total resection of an insular tumor, an insular glioma? I mean, they can do a really good resection, but I'm not so sure they can do a
true, 80%, yes.
Yeah, true gross total resection. I mean, we don't get true gross total resections unless somebody does lobectomy.
Yeah, sure. But probably it's better than a single biopsy plus.
Oh, there's no question. No question. No question.
Yeah.
Victor, may I have a question? We've been working with a new sequence on MRI called amide protein transfer, APT. Have you or anybody you've been working with using amide protein transfer to evaluate low-grade, anaplastic, and high grades? Because it's a sign of proteinaceous material, DNA, RNA, and it may show early de-differentiation from a low grade to a anaplastic by its appearance. Have you worked with APT?
No, because you got to remember that when I started semi-retired, I worked for Kaiser, and so they don't have that. And I've been doing telemedicine only for the last 6 years, I think. So they don't, they have some new techniques for washout of dye for looking at the permeability for radiation necrosis versus tumor, but I have not seen anything else. But UCSF would be the place, whether they're doing that or not.
Thank you.
Yeah.
Anybody else have any questions?
Well, that was, if no one else has any questions, I really thank you, Victor, for presenting this to us. I hope that since '77, I can get you over to Budapest after this pandemic is over with, because Budapest has changed tremendously since 1977. And I think
I never saw much of Budapest because when we came in, my wife and I had different visas, and so I had to leave. I had to leave earlier than she did. So they kicked us out of the hotel. This is 1977. And we spent some time in a police office with a light bulb above it. And they finally put me up at the cancer center had some housing. And so, yeah, it was terrible. I mean, we get on the train to Vienna, and Ellen's worried that that we're going to get picked up. So someday I'd like to see Budapest.
Things have changed, I promise you that. I think my colleagues in Hungary would agree with that. So again, thank you for being this keynote speaker for our lecture series. When we have time, I'll sit down with you and tell you about what we're doing in Budapest and the center that we've developed. So thank you again. Thank you for my Hungarian colleagues, and thank you, Dr. Erdős, for being the moderator today. Before you came on, we had a Hungarian neuro-oncology neurosurgeon also give a summary of glioblastoma. good review summary. But
I watched some of the slides. I couldn't understand the language, but I watched some of the slides.
Well, again, stay safe, Victor, and
All right.
thank you for your mentorship over the years. Thank you very much.
Take care, everyone. Yes.
Bye-bye.
Stay well. Bye-bye.
Thank you.
Thank you.
Thank you.
Köszi erős, Lordand, ügyes voltál.
Ja.
Hát ez tényleg a világ legsikeresebb olyan szakmai idegonkológus. Hát kicsit bonyolult volt az előadása, de érdekes nekem. Mi is benne voltunk ebben a kísérletben, de sajnos egy év után nem tudtunk egy beteget rárakni, mert nehéz volt. Szóval nehéz volt egy anaplastikus recurrent asztricitomát berakni. Szóval én köszönöm szépen mindenkinek, akkor 2 hét múlva, who's the next lecture in 2 weeks? Szóval Harvardból lesz egy ember, aki Josh Klein, aki tényleg egy nagyon ügyes és okos srác, aki, what is he going to be talking about? És akkor 2 hét múlva a következő adás. Köszönöm szépen, Ricsi.
Mi köszönjük.
Köszönjük, fantasztikus volt.
Bocsánat, még kérdés lehet kérdezni?
Bármit lehet kérdezni.
Jó napot kívánok, Ambrus Mónika vagyok. Én orvosan hallgató voltam, és most végeztem a SOT-én. És lenne egy gyors kérdésem, hogy a pseudotumor progression, ami előjött az első előadásban, hogy azt úgy értettem, hogy a PET-tel lehet megkülönböztetni, és ez ilyen 3-6 hónap után derül ki, hogy valójában pseudotumor volt-e, vagy nem. És most ezt a MI a kezelést dr. László Mekler mondta, hogy azt esetleg lehet-e használni arra, hogy megkülönböztetjük a pseudotumor progression-t a valódi tumor progression-tól?
Monika, használni mi a MRI-t?
Nem, you mentioned the MI protein transfer for an actual study to differentiate low grade and high grade. And we brought up the pseudo progression in tumors that occurs after treatment. And a lot of times, even though pseudo tumor progression is a natural occurrence, sometimes it is misdiagnosed. So we assume pseudo, even though it's actual tumor progression. Is the MI protein transfer a plausible way to actually make sure that it's actually pseudo tumor progression and we're not telling the patient he's safe?
Jó kérdés, Monika. A Nandi Pinte is itt van a közönség között. Eddig, ami 6-700 betegünk van, aki APT-t csináltunk. Ez egy ilyen Philips szekvencia, de megmondom őszintén, a GE-nek is megvan, most tudtam meg. De a Philips megadta az engedélyt nekünk, hogy használjuk ezt a APT-t. És érdekes módon tényleg nagyon sok beteg, ahol egy low-grade gliomátom, amikor magas malignitás van, akkor látszik a változás. Hasonló képű, mint egy PET, de teljesen más, mint a PET, csak a színek olyanok, piros, narancs, sárga. De sajnos láttunk APT pozitívást a infekcióba, a posztoperatív infekció, és epilepsziás gós. Szóval amikor valakinek egy epilepsziás rohama, akkor is érdekes módon az APT, mondom, egy eset magas lett. De a kérdés az, hogy a radiation necrosis versus pseudoprogression versus progression. Én azt hiszem, hogy ezt át fogjuk nézni, hogy pontosan, mert megvan a patológia, az a klinikai esetek nálunk van. Én azt hiszem, a progresszió és a sugárnekrózis között lehet kimutatni, hogy a APT különbözteti a kettőt. A kérdés az a pseudoprogression, ami általában 4 és 10 hét után jön be, és 20-30% a betegeknek megvan, aki kap sugárzást és citostatikum, temozolomide, és ezt nem tudjuk biztosan. Van egy érzésem, hogy nem fog segíteni, de nem vagyok biztos benne, mert adat megvan, de nem néztük át pontosan ezt a kérdést. De mikor kijössz hozzánk, vagy dolgozol a Mind Institute-ba, akkor ez a te munkád lesz, jó?
Szívesen el is kezdenám most, hogyha lehet.
Jó, akkor el van intézve. Ricsi, légy szíves.
Oké.
Számokat, megvan az első kutatás APT-vel, jó?
Szuper, szuper.
Köszönöm, Mónika, hogy voltál.
Írjál Mónika a Lacinak, és ő továbbítja majd nekem, jó, az e-mailt?
Jó, nagyon szépen köszönöm.
Jó, köszönjük szépen.
Sziasztok.
Akkor sziasztok. További jó munkát.
Sziasztok.
Jó, szervusztok.
Szia.